Welcome to this walkthrough of problem number 322, coin change. In this problem, we'll explore how to determine the minimum number of coins needed to make a specific amount, given an array of coin denominations. This is a classic dynamic programming problem that tests your problem-solving skills and understanding of optimization techniques. Let's dive in. In this problem, you are tasked with finding the minimum number of coins needed to make up a given amount of money. You are provided with an array, coins, which represents the denominations of the coins available, and an integer, amount, which is the target value you need to achieve. If it's not possible to make up the amount using the given coins, you should return -1. Importantly, you can assume that there is an unlimited supply of each type of coin. For the input, the coins array will have between 1 and 12 elements, and each coin value will be a positive integer up to 2 to the power of 31 1. The amount is a non-negative integer that can go up to 10,000. The output will be a single integer representing the minimum number of coins required, or -1 if it's impossible to form the amount. Let's look at some examples to better understand this problem. In the first example, the input coins array is 1, 2, 5, and the target amount is 11. The output is 3, because the amount 11 can be made using 3 coins, 5, 5, and 1. In the second example, the input is coins equals 2, and amount equals 3. Here, the output is -1, as it is not possible to form the amount 3 using only coins of denomination 2. This demonstrates that the solution must handle cases where the target amount cannot be achieved with the given denominations. In the third example, the coins array contains just one denomination, 1, and the target amount is 0. Let's see what the output is for this scenario. For the third example, the output is 0, as no coins are needed to make up the amount 0. This highlights one of the edge cases. If the target amount is 0, the result is always 0 because no coins are required. Additionally, there are other constraints and edge cases to consider. For instance, if there is only one coin denomination, the solution depends on whether the target amount is divisible by that denomination. If no combination of the given coins can sum up to the target amount, you must return -1. Finally, for large values of amount or when the denominations in coins are relatively small, the solution must be efficient to avoid timeouts. These constraints emphasize the importance of designing an optimized approach to solve the problem. To tackle the coin change problem, we first consider the brute force approach. The intuition here is straightforward. We try all possible combinations of coins to determine the minimum number required to make up the given amount. Using recursion, we explore every way to subtract each coin denomination from the target amount. For example, with coins 1, 2, 5, and an amount of 11, we can recursively subtract 1, 2, or 5 from 11 and calculate the coins needed for the remaining amount. The base case occurs when the amount becomes 0, or no coins are needed, so we return 0. If the amount becomes negative, it indicates an invalid solution, and we return infinity. However, this approach is highly inefficient due to redundant calculations, leading to an exponential time complexity of s to the power of n, where s is the amount and n is the number of coins. This inefficiency motivates us to explore a more optimized solution using dynamic programming. In the dynamic programming bottom-up approach, we avoid redundant calculations by systematically building solutions for smaller subproblems. By storing these intermediate results, we can compute the minimum coins needed for any amount efficiently. Let's see how this works in detail. In the bottom-up dynamic programming approach, we start by initializing a dp array where dp, I, represents the minimum number of coins required to make up amount I. To begin, we set dp 0 equals 0 since no coins are needed to make amount 0. For all other amounts, we initialize the entries in the dp array to infinity, indicating that they are initially impossible to make. We then iterate through all amounts from 1 to the target amount and use the recurrence relation, dp I equals min dp I coin plus 1 for all coins if I equals coin. This means that for each amount I, we check all the coins and find the minimum number of coins required to form that amount. For example, with coins 1, 2, 5, and an amount of 11, we compute values step by step. For dp 1, we only use the coin 1, so dp 1 equals 1. For dp 2, we compare using 1, 2 or 2, 1s, resulting in dp 2 equals 1. Similarly, for dp3, the minimum is achieved by using 1, 2 and 1, 1, so dp3 equals 2. Eventually, for dp11, we combine the results of smaller subproblems to find the minimum number of coins as 3. This approach minimizes redundant work and ensures we compute the result for all amounts systematically. The time complexity is O, amount asterisk n, where n is the number of coins, and the space complexity is O, amount. In contrast to the bottom-up approach, the top-down dynamic programming method relies on recursion combined with memoization. Here, we recursively break down the problem for smaller amounts and store the results in a memoization table to avoid redundant calculations. While this approach has the same time and space complexity as the bottom-up version, some developers find it simpler to implement, as it follows a natural recursive structure. However, it may involve additional overhead due to recursive calls. Among the approaches discussed, we chose the bottom-up dynamic programming strategy as our solution. This method is intuitive, efficient, and avoids the overhead of managing recursive calls. By solving all subproblems in a systematic and iterative manner, it provides clarity and is easier to debug and optimize compared to the top-down approach. The brute force approach, while conceptually simple, is infeasible for larger inputs due to its exponential complexity. In summary, the bottom-up dynamic programming approach strikes the perfect balance between efficiency, clarity, and scalability. It enables us to compute the minimum number of coins for all amounts from 0 to the target amount in O, amount asterisk n, time, making it a practical and reliable solution for this problem. In this problem, we're tasked with finding the minimum number of coins required to make up a given amount, using the provided coin denominations. If it's not possible to form the amount, we return -1. To tackle this, let's start by breaking the problem into smaller steps. The brute force approach begins with a recursive perspective. At each step, we have the option to use any denomination of coin. By subtracting the chosen coin's value from the target amount, we reduce the problem to finding the minimum coins required for this smaller amount. For instance, with an amount of 11 in coin denominations 1, 2, 5, we can create smaller subproblems for amounts 10, 9, and 6, depending on whether we use the coins 1, 2, or 5, respectively. However, we need to ensure that our recursion terminates. If the amount becomes 0, it means no more coins are needed, so we return 0. On the other hand, if the amount goes negative, it's an invalid path, and we return infinity to signify that this route doesn't lead to a solution. To continue, the recursive approach explores all possible paths. For each coin in the list, we calculate the result of reducing the amount by that coin's value and recursively solve the smaller problem. Once all paths are explored, we take the minimum result from the valid ones and add 1 to account for the coin we used at this step. Finally, we return the minimum number of coins required. If no valid solution exists, meaning all paths lead to infinity, we return -1. To implement this, we define a recursive function mincoins, amount, that calculates the minimum coins needed for a given amount. Within this function, we iterate over each coin in the list and call mincoins, amount, coin. The results from these recursive calls are stored, and we choose the smallest one, adding 1 for the coin used in this step. A critical aspect to handle is when no valid solution exists. In such cases, we return -1 to indicate that the target amount cannot be formed with the given denominations. There are important edge cases to consider. If the list of coins is empty, it's impossible to form any amount, so we return -1. Similarly, if the target amount is negative, we also return -1, as no combination of coins can result in a negative value. Now, let's reflect on key insights from this approach. The brute force method generates an exponential number of recursive calls because each coin choice creates a new branch, and the recursion depth depends on the amount. This leads to overlapping subproblems where the same amounts are recalculated multiple times. For instance, mincoins, 6, might be computed repeatedly in different branches. To optimize this inefficiency, we can use memoization or dynamic programming to store and reuse results of previously computed amounts. This avoids redundant calculations, significantly improving performance. The main data structures involved include the list of coins, which is used to iterate through available denominations, and a memoization table, such as a dictionary or array, for storing pre-computed results during optimization. Let's break down the key operations in this approach. First, recursive calls are made to reduce the problem size by subtracting the value of the chosen coin from the target amount. Second, base case checks ensure that the recursion terminates appropriately either when we reach an amount of 0 with a valid solution or when the amount becomes negative, indicating an invalid path. Third, the algorithm calculates the minimum result from all recursive paths, ensuring we use the fewest coins to form the amount. However, this brute force strategy has significant computational costs. Its time complexity is n caret amount, where n is the number of coins, as each amount generates multiple recursive calls. The space complexity is amount, due to the recursion stack. To improve this, we can implement memoization. By storing already computed results of min coins, amount, in a dictionary, we avoid recalculating the same values. Alternatively, dynamic programming can be used to solve this problem iteratively. Starting from smaller amounts and building up to the target, we store the minimum coins required for each amount in a table, ensuring an efficient solution. To illustrate this process, let's walk through an example. Suppose we have coins 1, 2, 5, and need to form the amount 11. We start by solving min coins 11. First, we try using coin 1, which reduces the problem to 1 plus min coins 10. Next, we try coin 2, leading to 1 plus min coins 9. Finally, we try coin 5, resulting in 1 plus min coins 6. Each of these paths is explored recursively until the amount becomes 0, at which point we return 0, or the amount becomes negative, which invalidates that path. After evaluating all possible paths, we take the minimum result. In this example, the minimum number of coins required to form 11 is 3, achieved using coins 5, 5, and 1. This example highlights how the algorithm systematically explores all options to ensure the optimal solution is found. This implementation solves the coin change problem using dynamic programming, DP. The main idea is to use a DP array where each index represents the minimum number of coins needed to make up that specific amount. First, the DP array is initialized with a very large value, infinity, representing that initially all amounts are considered unachievable. The base case is DP 0 equals 0, as no coins are needed to form the amount 0. Next, for each coin in the given coins list, the algorithm iterates through all amounts from coin to amount. For each amount x, it calculates the minimum coins needed by comparing the current value of DP x with the value of DP x coin plus 1. Here, DP x coin plus 1 represents using one coin of the current denomination and the optimal solution for the remaining amount, x coin. After processing all coins, if DP amount is still infinity, it implies that the amount cannot be formed using the given denominations, and the function returns -1. Otherwise, it returns DP amount as the minimum number of coins required. This solution has a time complexity of n*m, where n is the size of the coins array and m is the amount. The space complexity is m, due to the DP array. This is the Java implementation of the coin change problem, LeetCode number 322. The logic mirrors the Python solution, using dynamic programming to compute the minimum number of coins needed to make up a given amount. Key differences include the use of Java's arrays.fill for initialization, type specifications for arrays and variables, and the math.min method for comparison. The solution handles the base case where the amount is 0 and iterates through each coin to update the DP array. If the amount cannot be made up, the method returns -1, otherwise, it returns the minimum number of coins required. To solve the coin change problem, our goal is to determine the minimum number of coins required to form a specific amount of money using the given denominations. If it's not possible to form the amount, we return -1. The approach we use to solve this is dynamic programming. Let's consider an example where the coins available are 1, 2, 5, and the target amount is 11. First, we initialize a DP array of size amount plus 1. This array will help us track the minimum number of coins needed for each amount from 0 to 11. Initially, we set DP 0 to 0 since no coins are needed to form an amount of 0, and we set all other values to infinity, float, INF, because we haven't computed their values yet. At this stage, the DP array looks like this: 0, INF, 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 INF. This initialization sets the stage for us to iteratively calculate the minimum coins required for each amount. Now we start processing each coin. For the coin with a value of 1, we iterate through all amounts from 1 to 11. At each step, we update dp x using the formula dp x equals min dp x coin plus 1. This ensures that we consider the current coin and keep track of the minimum coins required. For example, dp 1 becomes 1 since we only need one coin of value 1. Similarly, dp 2 becomes 2, and this pattern continues until dp 11, which becomes 11. At this point, dp is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Next, we process the coin with a value of 2. For each amount from 2 to 11, we again update dp x. For instance, dp 2 becomes 1 because it's more optimal to use one coin of 2 instead of two coins of 1. Similarly, dp 3 becomes 2, and this pattern continues, resulting in dp 11 being updated to 6. After processing coin 2, the dp array becomes 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Next, we process the coin with a value of 5. Starting from amount 5, we update dp x for each amount up to 11. For example, dp 5 becomes 1 because one coin of 5 is more efficient than using smaller denominations. Similarly, dp 6 becomes 2 by adding one coin of 5 to the amount 1. This process continues until dp 11, which becomes 3, as the optimal solution is to use two coins of 5 and one coin of 1. At the end of this step, the dp array looks like 0, 1, 1, 2, 2, 1, 2, 2, 3, 3, 2, 3. The value at dp 11 tells us that the minimum number of coins required to make up the amount 11 is 3. Thus, the final result for this example is 3. Let's consider a simpler example with coins 2 and a target amount of 3. Initially, the dp array is 0, INF, 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 indicating that we haven't computed the minimum coins for amounts 1, 2, or 3 yet. We then process the coin with a value of 2. For amount 2, we update dp 2 to 1 because we can form the amount using one coin of 2. For amount 3, however, we find that it is impossible to form the amount using only the coin with a value of 2, as there's no valid combination. This leaves dp 3 unchanged at infinity, INF. The final dp array is 0, INF, 1, INF. Since dp 3 remains infinity, we conclude that it's not possible to form the amount 3 with the given coins, and we return -1. Finally, let's look at a more complex example where the coins are 186, 419, 83, 408, and the target amount is 6,249. We initialize a dp array of size 6250, with dp 0 set to 0 and all other values set to infinity. We then process each coin one by one, updating the dp array to reflect the minimum coins needed for each amount up to 6,249. While the detailed calculations for each coin are omitted here, the process remains the same. For each coin, we iterate through the amounts and update the dp values using the dynamic programming formula. After processing all coins, we look at dp 6,249 to determine the result. If it contains a finite value, that indicates the minimum number of coins required, otherwise, it means it's impossible to form the amount, and we return -1. The final answer depends on the result stored in dp 6,249. To analyze the time complexity of our solution, let's first break it down into its key components. The outer loop iterates through each coin in the given coins array, so the number of iterations here equals the number of coins, denoted as n. Within this outer loop, there's an inner loop that processes amounts ranging from the value of the current coin up to the target amount. The number of iterations in this inner loop is proportional to the amount. Since every iteration of the inner loop involves a simple update to the dp array, which is a constant time operation, the total number of operations is the product of the outer loop and inner loop iterations. This gives us a total time complexity of n asterisk amount, where the algorithm scales with both the number of coins and the target amount. This efficiency stems from the linear processing of amounts for each coin, avoiding redundant calculations. Now turning to space complexity, the main factor is the DP array, which is used to store the minimum number of coins required for each amount from 0 to the target amount. Since the array has a size of amount plus 1, the space complexity is O, amount. Beyond this, no additional data structures of significant size are used, so the space consumption remains minimal. Examining the algorithm under different scenarios, in the best case where the target amount is 0, the computation ends immediately, resulting in a time complexity of O(1), while still requiring O, amount, space for the DP array. In both average and worst cases, the algorithm processes all coins and amounts, giving a time complexity of O, an asterisk amount, and space complexity of O, amount. This consistency in complexity highlights the robustness of the dynamic programming approach. Let's consider how this dynamic programming approach compares to a naive brute force solution. In a brute force approach, we would recursively explore every possible combination of coins to form the target amount. For each amount, this leads to exponential branching with a time complexity of O, n caret amount, given that each recursive call considers n coins. This is incredibly inefficient, especially for larger inputs. Dynamic programming, by contrast, takes advantage of overlapping subproblems in memoization to eliminate redundant calculations. This reduces the time complexity to O, an asterisk amount, making it far more efficient. To understand this mathematically, the outer loop runs for n coins, and for each coin, the inner loop processes approximately amount iterations. Each iteration updates a value in the DP array in constant time, resulting in a total of O, an asterisk amount, operations. The space complexity remains O, amount, as it depends solely on the size of the DP array. To summarize, the dynamic programming solution achieves a time complexity of O, an asterisk amount, and a space complexity of O, amount. This represents a significant improvement over the brute force approach, which has an exponential time complexity of O, n caret amount. By avoiding redundant calculations and leveraging memoization, the dynamic programming approach efficiently solves the problem even for large inputs. This contrast underscores why dynamic programming is such a powerful tool for optimization in problems involving overlapping subproblems and optimal substructure. When working on problems like coin change, there are a few common mistakes that can trip you up. One of these is failing to account for all possible combinations of coin denominations. For instance, if you always start with the largest denomination and don't explore other paths, you might miss the optimal solution. To avoid this, you can use recursion, dynamic programming, or backtracking to systematically explore all combinations. Another issue is running into infinite recursion or a stack overflow. This happens when you forget to include clear base cases in your recursive solution, like stopping when the amount is 0 or negative. Without these, your program might crash. Finally, relying on a brute force approach can be highly inefficient for large inputs. Brute force often recalculates the same values repeatedly, leading to time limit exceeded errors. Using memoization or dynamic programming can help optimize your solution by avoiding redundant calculations. Additionally, it's important to handle edge cases properly. These might include scenarios like an amount of 0, a single coin denomination, or a situation where it's impossible to form the target amount, such as making 3 with only coins of 2. Ignoring these edge cases can lead to incorrect results. Testing your solution with diverse examples is key to ensuring its robustness. Another common pitfall is misunderstanding the problem constraints. For instance, you might overlook the maximum allowed coin count or the range of the target amount. This could make your solution unnecessarily complex or inefficient. Carefully reading and understanding the constraints in the problem description helps you tailor your approach and avoid wasted effort. This type of problem is frequently used in interviews to test your dynamic programming skills, so it's important to master this technique. Specifically, you should know how to identify overlapping subproblems and optimize your solution with memoization or a bottom-up approach. Interviewers will also expect you to clearly explain the trade-offs in your solution, such as the time and space complexity. For example, a recursive solution with memoization typically has a time complexity of O, n asterisk k, where n is the target amount and k is the number of coin denominations. Communication is just as important as coding, so articulate your thought process clearly, including why you chose a particular method and how you plan to handle edge cases. Using small, simple examples to demonstrate your logic can also make your approach easier to understand for both you and the interviewer. This problem is part of a broader category of dynamic programming challenges, and understanding related problems can deepen your knowledge. For example, LeetCode 322, the classic coin change problem, focuses on finding the minimum number of coins to make a given amount. Its variation, LeetCode 518, asks for the total number of ways to make up the amount, which shifts the focus to counting combinations. Another related problem is LeetCode 70, climbing stairs, where you calculate ways to reach a target step, similar in structure to coin change. LeetCode 139, word break, deals with partitioning a string and shares parallels with partitioning amounts in coin change. Exploring these problems can help you recognize common patterns and refine your dynamic programming skills. There are several approaches to solving the coin change problem, each with its own advantages and trade-offs. Recursive backtracking, for instance, is straightforward to implement and helpful for understanding the problem, but it becomes inefficient for large inputs due to repeated calculations. Top-down dynamic programming, or memoization, improves efficiency by storing intermediate results. Many programmers find this approach intuitive, but it can consume significant memory depending on the size of the memoization table. Bottom-up dynamic programming, on the other hand, is often more space-efficient and avoids recursion altogether. However, setting up the DP table and ensuring correct transitions can be tricky and prone to errors. Lastly, breadth-first search, or BFS, is another option, especially when you're looking for the shortest path, such as the minimum number of coins. The downside is that BFS can require a lot of memory for large target amounts, so it's important to weigh these considerations when choosing your approach. Great job making it to the end of this solution for problem number 322, coin change. In summary, we tackled this problem by exploring different approaches, including brute force and dynamic programming, and highlighted key lessons about optimization and problem-solving strategies. Remember to practice similar problems to solidify your understanding. Thank you for watching, and don't forget to like, comment, and subscribe for more programming content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!